even looking at it, and it's kind of like I can go this way, you see. This is okay. If I go back, just realized yesterday. You know? All right.
So it's great to have our own Artan Sheshmani talking about powerful technology and some
Thanks so much for the introduction. I would like to thank the committee of ICBS for inviting me to speak in this amazing congress. So this is based on two series of joint works. One is the one which is the focus of my conversation today is with Baranovsky in Miami, Ludmil Katzarkov and Maxim Kontsevich. And it's really based on a series of joint work with Borisov, Dennis Borisov, Ludmil Katzarkov, and Professor Yau. So I'll just set the motivation for this problem that we are solving. Motivation comes from string theory. It's called S-duality modularity conjecture. And I would not talk about physics because I don't understand physics, but I will just give you the translation of this problem in physics. You have a Calabi Yau threefold, and you, with the Picard group, and you pick an ample divisor, an element of the Picard, ample line bundle. You pick an integer, k, positive integer, and ample line bundles are associated with divisors, and given that h1 of the Calabi Yau is 0, the moduli space of such divisors is a projective space. It's the linear system of k times L. You pick some generator of integral h4 cohomology theory of x. It's isomorphic to z. Let's say its generator is L. So these are generators of curve classes. And then using this information, I would like to construct a moduli space of sheaves. For sheaf moduli, you need to fix the Chern character. So this is all trying to tell you what our sheaves are. Okay, so these sheaves have fixed Chern character. I pick two integers, I and n, fix them, and the Chern character is given like this. Every coherent sheaf on a Calabi Yau 3 has Chern character from Chern 0 to Chern 3. Our Chern 0 is 0, so these sheaves are not supported on all of the variety. They are portion sheaves. Support dimension of the support is less than the support ambient dimension, which is complex dimension 3. First Chern character is dimension of their support, class of their support is H, and H is an element of the linear system that I just fixed, and some curve class and some Euler characteristic. Let MCX be the moduli space of Gieseker semi-stable sheaves, and Gieseker semi-stability is with respect to a polarization. Here it is the ample line bundle L that I just fixed. Okay. This is the picture. You have a smooth Calabi Yau threefold. You have surfaces on it. The surfaces belong to a linear system. You have sheaves supported on this surface, on these surfaces. And these surfaces, because they belong to the linear system, they are not necessarily smooth. They can deform in the linear system. They can become as singular as possible. There is a notion of invariant that you can associate to such moduli space, Donaldson-Thomas invariant. If the semi-stability and stability are the same, then we have the usual Donaldson-Thomas invariant. But if we consider semi-stable sheaves also, there is a generalized notion of Donaldson-Thomas invariance. And these take values in rational numbers. And this is due to the work of Joyce and Song. So these Donaldson-Thomas invariants are numbers each time that you fix a Chern character, and as you can see, linear system is fixed, H is an element of it, so as soon as I fix I and N, I kind of controls the curve classes, and N controls the Euler characteristic of the sheaf. Each time I fix I and N, I get a number. And then I let I and N vary, I get many, many numbers, infinitely many numbers. And then I put them in an infinite sum. This is the partition function of generalized Johnson-Thomas invariants. The partition function looks like a vector the way I have written it. So I is on the left-hand side. I fix I, then on the right-hand side, I just let N vary. So for the string theories, because I know string theories also is sitting in here, these are the zero instanton numbers. So these are kind of only appear on the third chain character. Okay. So tensoring this moduli space with O plus or minus L, our ample divisor, induces an isomorphism on the moduli space. The moduli space doesn't change, but the partition function will see that. So the partition function, the sum that I just described, gets shifted by some power of Q. Okay? So S-duality modularity conjecture is following way. So as you see, when you twist this with plus or minus L, you can keep twisting, and actually after some enough many twisting, which is exactly K times L cubed, depending on what L is, then this partition function completely repeats itself. So it's like a vector, each component vector is an infinite sum. So if I construct this vector from 0 to 1 before it repeats itself, I get something like this. Each component is an infinite sum. And the S-duality modularity conjecture, which is actually given by string theorist Gayotto, Strominger, Yin, and Gayotto Yin also separately worked on it, basically says that this vector valued function, this vector, is a modular, it's a holomorphic modular form with modular weight minus 3/2. So each component is a scalar function, modular form of modular weight minus 3/2. And this shift on the cube, you can calculate it using whatever methodology, growth in Dickley-Monroth or whatever. This is the shift in the power of cube that you have. Okay. Modularity is important because if I give you an infinite sum, then modularity allows you to calculate any number, any Johnson-Thomas invariant, any coefficient in this infinite sum using Ramanujan's recipe from finitely many few lower degree coefficients. Otherwise, you run into a problem that you cannot calculate all of them by hand, and this is exactly the problem with Gromov-Witten theory. So we know that there are infinitely many Gromov-Witten invariants, or in the language of string theory, topological string amplitudes for all the genus, but we have only calculated them so far, 101 of them. Because they are not modular. Yes, yes. This is about higher rank. This is about higher rank. Yes, yes, that's right. That's right. This is about higher rank. Okay. The first time that I was given this problem was indeed by Richard Thomas. I was just done with my PhD. I went to University of Cambridge. Richard was on sabbatical there. And he gave me and my friend Amin Gulab, who both the same problem. Because he knew that we can't solve it. So, okay, so he said, you know, though you have sheaves supported on surfaces, and the surface is deforming inside the ambient Calabi Yau threefold, there is this amazing modular form that I want to prove. Of course, looking at all possible sheaves on the surface is a very difficult problem. So you need to start from rank 1 sheaves. Sheaf with respect to the ambient threefold is rank 0, but over its own support, rank 1 is the simplest possible sheaf. And then even simpler subset of these rank 1 sheaves are the ones which are given by sheaf of functions vanishing on curves and points on that surface. So ideal sheaf is the simplest possible sheaf, which is rank 1 on that surface. So we just try to count those things. We counted those things actually, and because we are not counting all sheaves, not all even rank 1 sheaves, and definitely not higher rank sheaves, we calculated infinitely many of these numbers in the partition function, actually, but we couldn't obviously prove any modularity. So my talk today is thinking about this problem for 15 years and kind of, maybe I can convince you that we can prove now modularity. Yeah. Yeah, that's right. Just want it to be as simple as possible. Yes. Yeah.
But both are just these powers. Right?
Yeah, the black box coefficients, exactly. Exactly. So these boxes are placeholders for these BT invariants. Okay, so in that situation, when the one-dimensional sheet over the support is ideal sheaf of some subscheme, one-dimensional subscheme of that surface, the moduli space of these things in some relative Hilbertism. So this is the picture, maybe it's easier. If I fix the surface, I still can vary the number Euler characteristic, which in this case would be Euler characteristic of structure sheaf of this one-dimensional subscheme, and the homology class of the curve, which we have on it. So this itself, for every fixed surface, has a moduli space, and that's the Hilbert scheme of curves on that surface. As the surface moves in its linear system, I get a relative Hilbert scheme. And so these invariants that we calculated are contribution of the relative Hilbert scheme to our overall partition function in S-duality conjecture. If the surface satisfies certain positivity condition, meaning if I look at this blue curve, it's a curve on the surface, but it's also a curve in the whole ambient variety. So there are two sheaves of functions that vanish on it. Sheaves of functions on H that vanish on it, that's the ideal sheaf on H, and sheaves of function on the whole variety that vanish on it. That's the ideal sheaf of this curve in the whole variety. So that's the ideal sheaf of Z with respect to X. And if that, twisted by the line bundle of functions having meromorphic poles along this divisor, has no higher cohomologies, then this moduli space is well defined. It has a self-symmetric perfect obstruction theory, etc., etc. Virtual dimension is 0. You can calculate invariance. So you can just see how restrictive our result was. Not only we were counting very simple sheaves, ideal sheaves on surfaces, we even needed positivity for them. Not every ideal sheaf satisfies us. No. It's quasi-small. Perfect symmetric two-dimensional. It's not this one. Okay, so to prove S-duality conjecture, the step 0 is what we did, which is basically just understanding what's going on. But then step 1, contribution of all sheaves of rank 1 with support on this surface, and proving modularity. Now, to prove the statement of a string theorist, you need to find a way to go from rank 1 to higher rank. And there is this magnificent work of Soheila Feyzbakhsh, who was postdoc of Richard, now she is in Imperial. They invented some kind of a wall crossing technology that allows you to go from rank 1 to higher rank. When I say higher rank on the surface, it's still torsion. But they don't prove anything about modularity. So if you know that these are modular, then maybe you can feed it into their technology and prove modularity in general case. Okay, so we need to understand this part, and that's my focus. Regarding this part, surface moving inside ambient threefold just freely in a linear system is a very, very special problem, a kind of very difficult problem. You can make it much easier by looking at other geometries. For instance, we can look at general rank 1 sheaves on surfaces in a threefold where the surface cannot just freely roam around. Let's say I have this is a problem we solved with amine. Let's say I have a K3 fiber threefold and I'm looking at rank 1 sheaves, not just ideal sheaves, all rank 1 sheaves supported on the fibers. There is this statement in complex algebraic geometry that if you have a surface which is a spool, and if you have a rank 1 sheaf on that surface, it is in fact a twist of ideal sheaf of points. So in that case, the moduli space is easy. We calculated partition function. The partition function is given by kind of these two functions. The top function kind of keeps track of how many of the fibers, when I fix the homology class of a curve, how many of the fibers contain J-holomorphic curves with that homology, because if the surface moves, you fix the homology class, it's not guaranteed that after deformations, it's any more supported by a holomorphic curve. So top partition function tells you for each fixed homology class how many of the fibers have holomorphic curves. That's the Borchardt famous result. The theta function, it's a vector valued modular form of weight 21/2. And the bottom part kind of counts contribution of points, because these sheaves can be vanishing on points too, contribution of points on the fibers, and this is Gauch's formula. So it's K3 fibration, this is weight 12, this is weight 21.5. You divide, you will get exactly weight minus 3.5, and that's the proof of S-duality. Petty numbers, yes. For arbitrary smooth. It's Mach modular, yes, it's Mach modular. Yeah. Yes, yes. It's infinite products. It's the cuspidal form. It's the cuspidal form. Okay, so this is something, it's more general than the original result, but it's still the geometry is very rigid. Then, related to talk of Rahul yesterday, there's these amazing objects called the stable pairs. This in the language of string theory are D6, D2, D0 branes. You can count them. They are very interesting objects. This is wrong. So they are curves with points on them but no points off them. So this is wrong. This is a bad picture. So that's what a stable pair is. Doesn't have points off of the curve. And because it doesn't have points off of the curve, it is in fact the sheaf theoretic in the vicinity of the Gromov-Witten invariant. So that's the sheaf theoretic translation of Gromov-Witten invariants. Gromov-Witten stable maps don't have points off of them. Anyway, so we calculated these things too, and the partition function of them also has certain other modularity, and we recovered Calabi Yau formula. Okay, so I'm showing you these results because when you simplify the geometry, you can do something, but original problem was never mentioning anything about this specified structure. The surface is allowed to move freely inside the ambient threefold. Okay, so
just
yeah.
on that, stable pairs interact with the nodes.
With the nodes, the stable pair moduli space should not interact with the nodes. So when there is nodes on the K3 fibration, that moduli space is ill-defined. So you need to blow up the fibration along those nodes. And then you leave the algebraic, projective category. We did a lot of things. You go into non-commutative geometry, things like that. So you need to find a way to count those things. Yeah. Good question, thanks. Okay. Again, structured about very rigidified kind of geometries. You can count sheaves and non-compact threefolds given by total space of a line bundle on the surface, and then you can count rank 1 or higher rank sheaves on that surface. And this, surprisingly, the localized Donaldson-Thomas invariants in this case relate to some combinatorial kind of Seiberg-Witten invariance of the surface, kind of coupled with some combinatorial coefficients, plus some other correction terms which we call nested Hilbert scheme invariance. So when you look at this non-compact threefolds and you look at sheaves, which could be, this picture is trying to tell you that the sheaf is supported on surface, but it can have thickening. So that's a sheaf supported on fattening of the surface. And then you realize that it counts somewhat Seiberg-Witten invariance of the surface plus these things, and these things are nested Hilbert scheme invariance. Okay, so it relates to Waffa-Witten invariance, and Martin yesterday mentioned this in his talk. Okay. Okay, yeah, so here's those correction terms. The correction terms, nested Hilbert scheme invariance, are actually counted not only curves on points on the surface, but nesting of curves on points on the surface. Okay, so anyway, so these are interesting. Later with Diaconescu and Yau, we thought of the very analog of this problem in one dimension higher. So I have a threefold moving inside some ambient fourfold, and in some cases, partition function of DT invariance of fourfold can be calculated. This was done at the time that Richard, Thomas, and Johnson O had not come up with their amazing virtual cycle. So this counting sheaves on fourfold was a mystery. So we needed to use some assumptions and things like that. Okay, and derive geometry. Okay, so these are the results that we had from the past. So let me focus on the original problem. I have a Calabi Yau, maybe compact, and I have a surface moving in a linear system on this Calabi Yau. Okay. For simplicity, we picked the surface in the Calabi Yau to be hyperplane section. Actually, if you count all rank 1 sheaves supported on hyperplane sections, then using the Phase-Bach and Thomas result, you can extend it to all other thicker surfaces, higher degree surfaces. Okay. One technology that we would like to use in here And a lot of this work is actually influenced by the amazing works of Rahul over these years, is taking advantage of this degeneration technique. So you would know what the moduli space looks like in here. You have a picture of it. Definition of the invariant is well defined, but basically you cannot calculate anything, let alone proving modularity about it. Your hope is that you take the Calabi Yau 3, you degenerate into a normal crossing singular variety. In our case, it would be two Fano varieties meeting along their anti-canonical divisor. And then you look at what happens to the moduli space when you degenerate. Maybe the moduli space over the special fiber of this family, degeneration family, is easier to understand. And if you count things in here, and if you can show deformation invariance for the whole family, you can reverse engineer the problem and say, I can recover invariance of the generic fiber from the special fiber. That's basically what degeneration technique tells you. Okay, so Rahul mentioned this in his talk yesterday. Let's say, for instance, you can pick quintic threefold and decompose it into a quadric and a cubic, or quartic and a P3 by decomposing the polynomials. This is formal way of doing it, so you can construct some four-dimensional smooth projective Fano variety with ample anti-canonical bundle. You can look at this trivial family over A1 and pick a section of the anti-canonical bundle of the fourfold times the structure sheaf of A1. This is basically trying to tell you for each point of A1, which is the base of this degeneration, S is a section of the anti-canonical bundle on that point. Yes, so should be. Yes, good, very good comment. Thank you. So then we would like this to be in a way, this projective variety P, Fano fourfold, to be in a way that for t not equal to 0, locus of the section of the anti-canonical bundle is a smooth K3 fiber. And for t equal to 0, it decomposes into two sections. Each section is a section of some given choice of a splitting of the anti-canonical bundle, L1 times L2. And 0 locus of each one of these sections, 0 locus of section of L1 is Y1, 0 locus of section of L2 is Y2, and we would like them to meet transversely along the divisor, anti-canonical divisor. Okay, so this is exactly an example of Rahul. Let's say you have the quintic threefold. You can degenerate it in this family, t times f5 minus some polynomial of degree 1 times polynomial of degree 4. And 0 locus for t not equal to 0 is a smooth Calabi Yau 3. For t equal to 0, this goes away. 0 locus of this thing is the union of 0 locus of this and that. That's basically quartic threefold, which is Fano, and P3, which is Fano. But the base locus of this whole family of quintics is the curve of singularities. So as Alexei mentioned, total space of this family is singular, and you need to modify. So you blow up the total space of the family. What happens is that this quartic part doesn't change. This one, the P3, will be blown up at that complete intersection. So some quasi-Fano. So that's the idea, and this is the picture. I like to draw pictures. So you have the threefold, Calabi Yau. You have the two Fanos meeting along the anti-canonical divisor. In this case, in the quintic example, this is a K3 surface. And the dream of degeneration technique in Donaldson-Thomas theory is the following. Donaldson-Thomas invariants of the generic fiber are the product of certain Donaldson-Thomas invariants of Y1 with relative condition along this divisor and Y2 with relative condition also along this divisor. And it is splits. The splitting is given by the choice of the splitting of the original Chern character. Now I should tell you what does the relative sheaf mean. The dt invariant of Y1 or Y2 relative to S is the dt invariant of coherent sheaves on Fano Y1 or Y2, which meet surface in the middle homologically transversely. Okay? Homological transverse intersection means if I take that sheaf, each one of these three sheaves are moduled over the structure sheaf of Yi. Tensor product of F with the structure sheaf of the surface should not have any non-vanishing torus. So homological transverse means derived tensor product is the same as usual tensor product, or derived restriction is the same as usual restriction. Clearly, this is an open condition in the moduli space of sheaves on Y1 or Y2. Obviously, I can come up with situations that a sheaf on here falls into this divisor, so it's not meeting the transversely. Therefore, the loci of sheaves with relative profile along the surface are open in the loci of sheaves in each one of the Fanos. And that's the whole amazing technology invented by Jun Lee. If you want to define invariants, you need to integrate over these relative moduli spaces. And you cannot define an integral over open non-compacted spaces. You need to come up with a compactification. So in the sheaf case, Jun Lee and Wu, Baoz and Wu, or I think he's here, in Xinhua, created this technology for ideal sheaves and under Pandit-Thomas stable pairs, and for curve counting theories, Gromov-Witten theory, Jun Lee invented this. So let me show you what the invention of Jun Lee was. So imagine, forget about sheaves, we are doing curve degeneration. We want to count a stable mass on a Calabi Yau 3. We degenerate it into a normal crossing singular variety, and we want to say, hey, so if I fix the curve class beta, then I can break it into beta 1 and beta 2, and the things are curves on y1, y2 that meet this surface in the middle transversely. So all I need to do, I kind of make sure they glue. They glue to each other nicely, so their profiles need to match. And this is what Rahul was saying yesterday, that Hilbert scheme of points comes into the picture because on this surface, all you see is the points. So the moduli space of all curves on this side and on that side that match is restricts to the Hilbert scheme of points on that surface. This is why Hilbert scheme of points becomes important. Okay, but obviously this is a good scenario because I can have a picture like this, that one of the curves or each one of the curves fall into the divisor. Then what can I do? Well, then Jun Lee tells you that indeed this is saying that the relative curves are open inside their moduli space. You need to compactify. So you compactify by pictures like this. You divide this picture into two halves, one for y1, one for y2. On the very boundary of this compactification, you try to force the curve to be transverse to the divisor S. And you need to show that counting of curves is the same as countings of curves like this, which become transverse after many bubblings. So each one of these bubbles are P1 bundles over S. So this is actually very easy construction. So basically you take this variety, take this variety, you blow up, you take the variety times A1, you blow it up along 0 point of A1 times the surface. So this is degeneration to the normal cone of that surface. And what it does is that it gives you a family. Generic fiber of the family looks like this half picture. A special fiber of that family kind of replaces every point of this with a P1 fiber. Because the curve fell into that divisor, curve would stretch into that bundle to bubble. That's the bubble. But then we are not talking about necessarily irreducible curve classes. It might be that curve is reducible, so it might stretch into here, but it might have some components which are still falling in the isomorphic copy of the divisor here. Well, Jun Lee then tells you need to do it again and again and again. And the whole proof of Jun Lee is basically tells you that after finitely many of these accordionic expansions, the curve becomes transverse completely, not only to the original surface, but every isomorphic copy of the original surface. So he does this on both sides of the picture, and then he glues. Okay? Blow up the intersection of these two things. That's basically what he's doing. Yeah, that's exactly what he's doing. Yeah.
It's a process of finite, right?
Exactly. It's a process which is finite, which is important. Two things are important. One, that I don't need to do this infinitely many times, very important. Two, that this curve, a stable map, remains stable into the accordionic expansion. This is very important. If it doesn't remain stable, then our moduli space is not well defined. Okay, so
Roughly, where's that finite?
in his case, he basically he shows you that he can stretch this, and eventually he has enough many markings into the bubbles that fix the automorphism of the component. Yeah. And then he will exhaust the markings, and then after that he doesn't need to. After he has exhausted the markings, and he will not see a picture where you have exhausted your marking and you have a curve whose automorphism is infinite. Already by that time the curve has become transverse. Ask Rahul. He's the expert. Okay. All right. So this is what he's doing, and these are called expanded degenerations. So, okay. So Lee and Wu did this for ideal sheaves and pondered upon the Thomas stable pairs. And it works nicely. So yes, when you did this and when you did have these boundaries for these compactifications, your moduli space on each one of these half pieces becomes pictures like this. You need to take a limit over all possible expanded degenerations, and after that, one thing you know is that you have these compactified spaces, and you can restrict the curve moduli space on each side to the divisor in the middle, and the divisors in the middle on S or any isomorphic copy of S are Hilbert scheme of points on that. So because you have two Fanos, after restriction you get two copies of Hilbert scheme of points, and this it could be N1 and N2, but you're just trying to glue them with each other. So you look at the diagonal embedding of one piece inside it, and then you look at basically via this diagonal embedding the Giesing pullback cycle of each one of the moduli spaces, the virtual cycle over the special fiber. And by deformation invariance, this is the same as virtual cycle of the generic fiber. So integrals match and everything works nicely. What's the problem? The problem is that this has an issue when you look at with general sheaves. Our sheaves are general sheaves. They are not ideal sheaves. They are sheaves which are torsion. Of course, following machinery of Jun Lee, you can see that after accordionic expansions, the sheaf stretches into the bubbles. And Jun Lee even tells you that after finitely many bubblings, the sheaf becomes transverse to all of the divisors. So this basically he does by, let's look at around here. Is it transverse? Is it not? He picks some neighborhood on the right and the left, Hilbert polynomial of the sheaf on the right, Hilbert polynomial of the sheaf on the left, he calculates them. Hilbert polynomial of the sheaf on the restriction to the divisor, he calculates them. He looks at f on plus f on the left minus the restriction. If this number is 0, the sheaf is transverse. So he basically constructs a polynomial, and he shows that as I keep bubbling, this polynomial, which sees the difference of Hilbert polynomials left and right hand on the divisor, monotonically decreases to 0 eventually. Polynomial, Hilbert polynomial sheaf on the right and on the left, minus Hilbert polynomial on the divisor. That works. Sheaf can always become transverse. But as you stretch the sheaf, it will not remain stable. The stability is an issue. So when you take the limit over all possible pictures like this, you cannot fix a polarization that gives you stability all the time. It's very easy to come up with destabilizing subsheaves of this stretched picture. So this degeneration technique for the past 15 years has not been generalized into all general sheaves because of this. This moduli space is ill-defined. It just doesn't work. No, and you can, but stability you cannot guarantee. You can. That is given by when the polynomial decreases to 0. When the sheaf becomes transverse, you can see that after finitely many ends, it becomes transverse. That's fine. Sheaf is not stable though. This sheaf, this moduli space is ill-defined. Good, yes. I didn't think about this, but maybe you can figure it out. Yes, good. Okay, so what? Maybe this. I didn't think about it, but let me tell you then how can we think about it. So instead, we do something else. Let us just forget about sheaves which are homologically transverse to the divisor. Let's look at all of these sheaves. Okay, all of this was trying to make sure that the derived restriction of the sheaf to the divisor is the same as usual restriction of the sheaf. Let's just not worry about that at all. So instead, we look at derived geometry, and we look at the moduli space of perfect complexes. Okay, so if these sheaves, two-dimensional with two-dimensional support, drive restrict to that divisor, they will not give you sheaves actually, they will give you two-term complexes. So the problem really, how can I compare two-term complexes with each other? What does that even mean? Okay, so here is what that means. So Let's change the point of view. Let's look at the DG scheme of rigidified perfect complexes. So instead of X is always for me a threefold, whether generic fiber or a special doesn't matter. I look at the perfect complexes which are rigidified. That means the determinant of that complex is a fixed line bundle on the Picard of that variety. Then I'm looking at objects who don't have negative X, and I'm looking at the ones whose trace map is isomorphic to C. Okay, that our sheaf satisfied is fine. So far it's fine. There is this result of Timo Shurek, Toen and Betsozi around 2015 that the derived stack of perfect complexes, rigidified perfect complexes, quasi-smooth. Quasi-smooth doesn't mean it's smooth. It means that it has a perfect two-term deformation obstruction complex, some object in the derived category with only two non-vanishing cohomologies that maps to the cotangent complex, and it's concentrated in this homological amplitude. Okay, so it's nice. So for each one of the Fanos, Y1, Y2, and the one in the middle, you can construct such DG stacks. Let us assume that these come with universal families. That's also possible. So then what? So now the divisor in each one of the Fanos, surfaces in each one of the Fanos is a divisor. So I can define derived restriction. If I take the perfect complexes or the universal family on each one of the moduli stacks, I can derive restrict it to the moduli stack in the middle. That's describing some derived restriction map. So this is what happens. The DG stack over the generic fiber degenerates into two DG stacks on the Fanos over the special fiber, which derive restrict to the middle. Okay. Now here is the result, a theorem which is many years ago by Turin, the famous Russian algebraic geometer, was predicted for vector bundles and so on. Later was proved by many people, Damien Kalak, Ben Bassat, and us too. We use it more down-to-earth way, that these derived restriction maps from each one of the Fanos actually define these things in here as a derived version of a Lagrangian. So the derived restriction map induces a map between relative tangent complex of each one of these maps to cotangent complex of the Fano moduli spaces with a shift in the derived category. And this map is a quasi-isomorphism of perfect complex. Okay? Think about the Lagrangian in a holomorphic symplectic manifold. If you have a two-form, non-degenerate symplectic two-form, you act on cotangent bundle of, you have the Lagrangian embedded, you act on tangent bundle, you're left with cotangent bundle. This is basically what that thing is. So in order to prove such thing, you need to look at these maps and write down exact triangle of canonical exact triangle of tangent complexes. You need to translate what these things mean. This is what I meant. It's very concrete for us. I can exactly say what these tangent objects are. And then we realize that the moduli space of perfect complexes on the anti-canonical divisor, which is a K3 surface, has a derived version of holomorphic symplectic two-form. It's actually, in the language of derived geometry, is a zero-shifted symplectic DG space. And this thing pulled back to the Fano moduli space, when I pull it back, actually maps to O. I mean, this is what the holomorphic symplectic two-form does to the product of tangent bundles. These are DG tangent bundles. And then you can actually use the argument that because these are Fanos, it satisfies a commutative diagram like this, but this term vanishes. So the pullback of the holomorphic symplectic two-form on the moduli space in the middle to each one of the Fanos becomes homotopic to zero. So this is a derived version of isotropicity of Lagrangians. This derived version of that. And then for non-degenerate property, basically, again, certain commutative diagram shows you that you get that quasi-isomorphism. Okay, so I'm not going to go into it. Now that you know each one of the Fano moduli spaces are in the language of DG geometry, Lagrangians, there is a statement by Pantev, Toen, Betsozi, and Vecchi that their fiber product over the middle moduli space is carrying a -1 shifted symplectic form, symplectic structure. If that's true, by the result of Joyce and Usi, Brav, Ben Bassat, this moduli space can always locally be written as a derived critical locus of some kind of Chern-Simons type of function. Locally, always. So if you look at, what does this moduli space look like? This moduli space is the pair of sheaves or perfect complexes on Y1 and Y2 that glue on the surface. This moduli space, if you look at around such things that glue nicely, derived geometrically, we don't need transversality. If you look at it around it locally, that local neighborhood can be written as a derived critical locus of some function. Okay, so now what? So I have a degeneration. It's a DG version of it. I know that this fiber is written as a derived critical locus. I know that this fiber also is written as a derived critical locus. This fiber, by the result of PTVV, originally even moduli space of perfect complex on Calabi Yau 3, -1 shifted symplectic. And this fiber also, both as derived critical loci. All I need to do, I need to somehow find a way of calculating DT invariance in here and DT invariance in here using this derived critical locus structure and show deformation invariance. Like how Jun Lee showed that the virtual cycles kind of match with each other over the generic and the special fiber, I need to do the DG version of that. Okay, so derived critical locus, what is it? If I have a function on a smooth scheme, the derived critical locus is represented by the Kojoule algebra. So you take the tangent bundle of that scheme, shift the tangent bundle, symmetric algebra of it with this differential of this function, gives you the Kojoule algebra. The cotangent bundle of this scheme is very easy. So induces a map from tangent bundle to O, and then if you compose with the Durham differential, it maps it to omega. So for this very easy case, the shifted symplectic structure on such thing, on such omega, is basically a statement about duality, self-duality of this complex. If W is a Calabi Yau variety, it is self-dual, so it's shifted symplectic. If not, it's not. Okay, so that's that. So what is important in here is that I should look at symmetric algebra of the tangent bundle, and I should construct a function out of it. And that function realizes my space locally as a critical locus. So let's do this for our moduli spaces. Let's say X in here is over generic or a special fiber, it doesn't matter. Let's pick some sheaf in either of the threefolds, generic or special. And let's look at that sheaf and formal neighborhood of that sheaf in the moduli space. I should look at this tangent deformation space. Deformation space of that sheaf is given by x1 and x2. Fiber-wise, my moduli space is a Calabi Yau. Generically, it's an honest Calabi Yau. A special fiber is a degeneration of that Calabi Yau. So I can assume Calabi Yau. So it's kind of deformation space is given by x1 and x2 via Serre duality. So these two terms are just enough for me to construct the Kojoule algebra and construct the functional. So how do I do it? I can construct some L infinity algebra. L1 term is x1, L2 term is x2, and then L infinity products are given by these symmetric polynomials on x1 that maps to x2. And then if I take the adjoint, I get linear maps from x1 to symmetric polynomials of u, x2, basically. And then I can put them all together, and this is my function. Okay? So you can actually show that the Kojoule algebra is given by the symmetric product of x1s and x2s and with the differential induced by this function. That's the Kojoule algebra. Look. Okay. Now why did I have these terms? So this is his theorem. This is this guy's theorem. So if you have something like this is your Fano fourfold. If you have some sheaf which is supported on here, right, you can push forward this sheaf and push it back. You will get back the sheaf, but you will see a term in here that sees the movement of this into the fourfold, basically. This is this sheaf tensored with conormal sheaf of X inside this projective Fano with a shift by 1. So if you apply R hum F to this exact triangle, you will see R hum FF. These are all these guys. On X, then you will see R hum back of the push forward of F, like that, but then you can use the left adjointness. So this becomes in here. This is R hum in the projective Fano. And then you can see R hum FF again. Conormal It's normal, but this shift by 1 becomes shift by minus 1. So this is actually tell you that even though these sheaves are fiber-wise sheaves, if you look at them as sheaves with one higher codimension inside the whole fourfold, their deformation theory will see the movement of the threefold into the fourfold. And this movement is given by the cohomologies induced by these terms in here. Not only that, you see that xiff in the fourfold sits in between u and u2, things like that, and x, again on x with 1 degree less. So whenever I have x1, I have an x0 that contributes. When I have x2, I have an x1 that contributes under Serre dual. So what am I saying this? Because Koszul algebra of these sheaves, so if I look at the moduli space of Fano fourfold, parameterizing sheaves one higher codimension, look at the local neighborhood of these things, this Koszul algebra, which is a symmetric algebra of the shifted tangent bundles, should see these terms with 1 degree less under Serre duals. So this is it. This is these W, these ones with canonical bundle are anti-canonical bundle, pop. Okay, so what is the point? I have 15 minutes. Okay. The point is this. So originally for the threefold moduli space, you can show that the L infinity algebra is the Koszul algebra induced by the polynomial I just constructed. And for Fano moduli space, this fails because of being Fano. So you need certain self-symmetry of this Koszul algebra. You don't have it for Fano. But the Fano moduli space and the algebra, L infinity algebra you construct on it, induces A dot of x. So it's not irrelevant of A dot of x. So this is the statement. So on the Fano, we can construct some modified L infinity algebra structure that sees all the terms, x of ff, and those other terms that see the fourfold. These blue terms always see the fourfold. And some new function. So the first piece just sees extensions on threefold, and this new function actually kind of sees all the normal bundle contributions. So this is a function. And then out of this, and I'm going very fast because I just want to give you a vibe of the output. So basically you can show that, okay, so I'm not going to prove this. You can show the following lemma. So you can see that this function g that you construct on the moduli space of sheaves with 1 codimension higher, on the whole Fano fourfold, itself has f plus that function, has a derived critical locus, and its derived critical locus as a DG algebra is quasi-isomorphic to the Koszul algebra of the fiber-wise moduli. This is the state. Okay, so I can relate some DG algebra on the fourfold to the DG structure sheaf of the Fano moduli space. So why on earth am I doing this? Because this is allowing me to give the DG version of deformation invariance. If everything comes from fourfold, it doesn't matter, right? If it doesn't matter if I'm on the generic fiber or on the special fiber, they must be the same thing. This is why we are doing this. So the trick is finding this function, and we found it, and derived critical locus of this we can prove is the isomorphic to Koszul algebra of the formal completion of the moduli space on the fiber-wise families of this degeneration. All moduli spaces. This is general. Okay.
Sorry.
Yeah.
So I should think of this G as encoding the Atiyah class somehow.
Algebra, yes. Algebra induced by Atiyah class of these sheaves, but into the fourfold. That's right.
Was that
It's
an existing interpretation of the Atiyah class?
it's a and what is the existing interpretation?
Is that
It's not exactly Atiyah class because it's basically you construct this function and these maps are partial derivatives of this function with respect to elements of u, w1 or w. So anyway, it's a little bit involved. Yeah. Yeah. That's right. It's new. It's new. But I don't think it's directly Atiyah class. It's just not directly Atiyah class. It's a mixture. These, so, so this part is the idea class. But it's more than idea class. Anyway. Yeah. Anyway. So, I didn't, anyway. Okay. So, fine. So we have now two DG algebras. Fiber, generic fiber and special fiber are related to the DG algebra on the fourfold level. So now I need to relate DT invariants. What's the DT invariants? Where are they coming from? So this is the language of quasi-BPS categories. If you have a family of potentials, this is F plus G. It's of course parameterized with respect to the sections. So remember, everything is made of sections of anti-canonical bundle on a fourfold. So it's a function of sections where I pick the section. And then the derived critical locus, the F part gives me the DG moduli space of rigidified objects on that fiber. And then Padarario and Toda came up with an kind of a description of what is called the quasi-BPS category. So what is that? You pick, it's basically the Z2 graded category of matrix factorization of the potential. So on each fiber you have a potential. You can construct the category of matrix factorizations. It's a curved DG category. I'm not going to get into it. And then this curved DG category has a Hochschild homology. You can construct a Hochschild complex from it. This Hochschild complex actually has a homology, and you can show that periodic cyclic homology of the Hochschild complex of the matrix factorizations actually, by the result of FMOF, is equal-isomorphic in Zariski topology and as a Z2 graded vector space to the cohomology of the twisted Durham complex of the modulized fiber-wise moduli space. So you have a potential. The potential comes from fourfold. Generic and special fiber are related to each other. Therefore, you have matrix factorizations on all the fibers. Each one gives you a Hochschild homology. And the periodic cyclic homology is equal to that. And that's in isomorphic fiber-wise to the cohomology of the twisted Durham complex. Okay? So what does that tell you? This is the result, that if I have a degeneration like this, then you can actually show that this periodic cyclic homology remains constant in the family. Because as everything comes from fourfold, it doesn't matter where in the family I look at it. And the dimension of this Z2 graded vector space remains constant. So this is the DG version of deformation invariance for the degeneration. Okay? So there is a statement that if the derived critical locus of a function, in here is our potential, lives inside the zero locus of that potential, then the cohomology or the twisted Durham complex is quasi-isomorphic to sheaf of vanishing cycles. So this sheaf of vanishing cycles studied by Davesh Malik and Toda and so on are indeed cohomologies induced by those things are exactly this cohomology induced by these periodic cyclic homologies. So the zero locus of this section is the reduced scheme sitting inside the derived critical locus. Okay, so computation of DT cohomology. Now that we know that we have cohomologies, we can calculate from this Hochschild periodic cyclic homology, generic and special fiber. We can ask, what does it look over the special fiber? I'm going to go on this very, very fast because I have 5 minutes only. So there is this work by Cunningham and Safranov that say if you have two Lagrangians in a symplectic, holomorphic symplectic manifold, and you have a choice of orientation, that means the choice of a square root of their canonical bundles, then you can come up with some deformation quantizations of these modules. So these are left modules over the ring of formal power series ring on the formal variable H. And then derived in tensor product of these two things is indeed the perverse sheaf of vanishing cycles associated to the Lagrangian intersection of those things. Okay? So we do the same thing. So, but using derived geometry, we have each one of the Fano moduli spaces. We need to choose an orientation data. That's the choice of a square root of universal canonical bundle. What that is, you look at the deformation obstruction complex. It has a local field resolution. You can take its determinant and you pick its square. and then you deformation quantize it to two left module flat CH power series modules over CH. And then you need to intersect them, so you need to dualize one, so that's R hum over O of H to O, but there is a shift that you need to take into account. So this kind of dual of this guy tensor the other guy is basically becomes like this. So I can put it this way. You have two moduli spaces, Fano moduli spaces. You can intersect them, derive geometrically by tensor product of their DG structure sheaf. But that's wrong. You need to tensor product their twisted DG structure sheaf. And the twisted one should respect the orientation. And the twisted one exactly is the choice of the square root of their DG canonical ones. That's this you can show that it's oriented. Actually, Toda has shown. Okay. So here is the conjecture that this derived tensor product, if you look at this module, you can use all the methodology you know how to calculate cohomologies, do the double-sided bar resolution or the bar resolution of this one or that one, calculate the cohomology. If you take those cohomology group and look at the alternating sum of the dimension of those groups, that should match with the product of the Donaldson-Thomas invariants of Y1 relative to S, Y2 relative to S, as if you could define them. So that's the number. Okay? So the Euler characteristic of this is the product of these two things. Okay. So let me show you in the last 5 minutes why S-duality modularity conjecture holds true. All of this was going a long way to tell you that because I don't have the notion of the relative DT theory, I need to somehow define it. Now we have defined it. Let me show you the generic picture. Let's say now, via this, these are defined. This product is defined. Let me show you what this product induces. Generically, you have sheaves supported on hyperplane sections of quintic. You have degenerated the quintic to quartic and the blow-up of P3. Generically, sheaves is supported on hyperplane section in here and hyperplane section in here. Again, generically, I can restrict F2 or F1 to the middle K3 divisor. I get a curve. This curve, because this one and this one are hyperplanes, this is a hyperplane section of quartic K3 surface. It's a genus 3 curve. And the sheaf restricts to it. So here we get this moduli space. There's nothing but moduli space of sheaves, pure sheaves, with one-dimensional support, generically, on curves of genus 3 on the quartic. Okay? I can in fact forget the sheaf information and map these sheaves to their support. That's a linear system of curves of genus 3 inside this K3 surface. And this is this Mumford support map. Okay? So let's now do some calculations. Using Grothendieck-Riemann-Roch, because this is Calabi Yau, virtual dimension of this guy is 3. Using Riemann-Roch, this is virtual dimension 3, 0. Virtual dimension 3, virtual dimension 3. This moduli space is actually a very famous one. Moduli space of pure one-dimensional sheaves on K3. This is Mukai's moduli. It's actually a smooth, and it's dimension 6. The smooth of complex dimension 6. So 3 dimensions mapping to 6 dimensions. Indeed, it looks like generically like a Lagrangian. But these are not dimension 3. These are just virtual dimension 3. That's why you need to use derived geometry to show they're Lagrangians. Okay? So, okay. So indeed, if I were naive, I would just take these two Lagrangians and intersect them with each other and calculate a number out of this intersection. Okay. So, yes. So this one, this moduli space, Mukai's moduli space is a holomorphic symplectic manifold with a non-degenerate 2 form. This moduli space is in fact, because sheaves of one-dimensional support on these curves, is the compactified Jacobian. For each fixed choice of a curve, it's a line bundle. If the curve is singular, it's a pure sheaf, but the curve is moving over the linear system, so it's a relative compactified Jacobian. Okay, so, and this has a section. And in fact, this holomorphic symplectic 2 form in here vanishes on this fiber. So not only these two are derived Lagrangian inside here, this thing itself over P3 is a Lagrangian pi ridge. So Lagrangian everywhere. A very beautiful picture. Okay, so it turns out that the relative DT invariance, which I define using this derived geometry, is the integral over the virtual class of these things. And what integral is it? Because virtual dimension is 3, if I wanted to follow the language of Richard, I should have integrated some degree 3 class. And turns out calculation shows that this degree class is nothing but pullback of a point from here. A point in here is codimension 3, so that's a degree 3 class. I can pull it back to here, I can pull it back to there, and then that's a degree 3 class. And then I can calculate that in integral. So the dt integrals have this localization property. So integral of pullback of this class is the same as integral of fiber of each one of the moduli spaces over that point. So what does the fiber look like? If I look at the left side of the picture, if I pick a point in here, that fixes a curve in K3 with sheaves on it. And if I look at the fiber of Fano in here on that, it's all the sheaves supported on hyperplane sections that pass through that curve. So in fact, the dt invariance of the left side of the picture is contribution of a pencil of cortex to dt invariance of y1. That's what it is. And on the right-hand side, I don't have a pencil. On the right-hand side, it's just one surface that passes through that curve. But because I blew up P3 at that complete intersection, that curve of singularities meets this curve of genus 3 at 20 points. The surface I get on the right-hand side is blow up of P2 at 20 points. Okay, so if I want to use the dream formula, dt invariance of generic fiber is the product of dt invariant on the left, which is a contribution of this pencil, times the dt invariant of sheaves of rank 1 on this blown up surface. But that's a relative Hilbert scheme of points. This is the first instant that modularity kicks in, because with amine, we showed that the dt invariance of relative Hilbert scheme of points is a modular form. So if you show modularity of contribution of this pencil, you're done with modularity of the generic fiber. Okay? So why is this pencil modular? Then I'm done with the time. Can I have 2 minutes? Okay. So here's how you show it, and this is one of those really cool things I learned from reading many hours papers of Rahul. So use the degeneration. Oh, okay. So this is why. If I take the Fano quartic fourfold and I blow it up along that base locus of that pencil, it suddenly, every point of that curve will be replaced by P1 below. So I get a K3 vibration on P1. And that's nice. So because my sheaves are supported on hyperplane sections, as soon as I blow up Y1, the Fano Y1 quartic, I can relate it to sheaves supported on K3 vibrations. And I showed you that in results, many years ago, we proved that those have modular partition functions. Okay, so how should I relate invariance of blow up of the Fano along that curve to my relative dt theory? Here is how you do it. Again, I learned this from Pandre-Pixton papers. Take the Fano, degenerate it into normal cone of that K3 surface. This is our fixed curve. I'm now only looking at a fixed curve because I'm calculating only contribution of that pencil on that fixed curve. If I degenerate it into normal cone of surface, I will get the Fano, I will get this P1 bundle over that surface. And this curve proper transforms to the zero section of this bubble. It's here. Now I take this whole fourfold family, blow it up at wherever the curve is. So this curve has a continuous limit into the degeneration. I take the closed subscheme given by this continuous limit, and I blow up the family over this closed subscheme. What it does is that over the generic fiber, it blows up the curve. So all of these generic fibers become K3 fiber threefolds. And over the special fiber, it blows it up where the curve is. So this piece gets blown up, this piece doesn't get blown. So then you have some situation where you have generically K3 vibration, and you have here quartic threefold remaining intact, and some blow up of this bubble. So use dt dream formula. Generic fiber dt invariance become relative dt invariance, which we wanted to calculate, times relative dt invariance of this blown up bubble. And again, this becomes the relative Hilbert scheme of points. So, okay, all I need to do, I take this and I write it as this divided by that. So, there you go. I put it in the original formula. Generic fiber quintic becomes the relative one, which is this divided by that. But this is modular form of weight minus 3/2. This is some modular form. This is some modular form. They have the same modular weight. The modular weight is 0. And that's it. That's the proof. Yeah. This is very special and it only works for quartic. I don't know because if I have I don't know I cannot answer this question because I was thinking how can I get this structure in a cubic? I don't get it.
The rank one, right?
Rank 1. But for higher rank, I feed it into Richard's proof, and it induces modularity of all the higher ranks. Thank you. Uh-huh. Uh-huh. So this is what Rahul was talking about yesterday. So one of the situations that such thing happens is that you degenerate the variety into something whose relative divisor is singular. Then the total space of the family will not be smooth. And then you need to blow up this thing. And then you will get actually three components. So you have a degeneration. It's a very bizarre combination of things. And to be honest, I actually don't know how that works. No, I don't know it. But this is what I asked him yesterday. He says it's possible. There's some pictures like this. So if you have variety and you degenerate into something, y1, y2 meet d like this, then you need to blow up this so it becomes some situation like this, something like this. But then I don't know how degeneration works actually. I have no whatsoever intuition.
The central fiber is rigid.
The center fiber, no, it doesn't matter. No. It's important for us that it is irreducible because this I don't know how to deal with, but reduced we don't need. Irreducible we need. At least I need. But Rahul can do anything, seems like everything. So, yeah.
We'll continue. Let's thank Artan.
Thank you.